In this video, we're going to be looking at a feature that is pretty much unique to reversible acid and base reactions. If we consider the forward direction here, we know that acetate, CH3COOH, is going to be acting as the acid in the reaction because water uses its lone pair to form a bond with the ionizable hydrogen here, breaking this bond, causing acetic acid to lose a hydrogen, and therefore it's acting as the Brønsted-Lowry acid in the forward direction. If we look at water, on the other hand, because water is using its lone pair to take a hydrogen from acetic acid and therefore gain a hydrogen in order to form H3O+, water is actually acting as a Brønsted-Lowry base. If we look at the reverse reaction, however, we see the roles of each molecule actually get reversed. So acetate, because of its negative charge, can use one of its lone pairs on the oxygen to reform the bond with one of the hydrogens on hydronium, therefore breaking this bond and returning it to a lone pair as it was with water. So here we actually see that acetate, because it is gaining an H plus back, is actually functioning as the Brønsted-Lowry base, and because hydronium is losing the hydrogen that it had previously gained as water, it is functioning as the Brønsted-Lowry acid when going in the reverse direction. This relationship is what we call a conjugate acid-base pair. So every acid and base ionization reaction is always made up of two conjugate pairs, which are two forms of the same compound that only differ based on whether they have or do not have an extra H+. For example, our first conjugate acid-base pair is acetic acid, where we can see that it has a hydrogen here that is easily ionizable, but then the conjugate base form, CH3COO-, has a negative charge in place of where the H+ would be. We can see that the other pair of acids and bases also follows this rule, where H3O+ has an extra easily ionizable hydrogen, whereas water does not have this extra hydrogen present, and therefore H3O+ and H2O function as the second conjugate acid-base pair. This is another way to know whether you have done the acid-base ionization correctly, because in our reactants we will always have an acid and a base, a compound that loses H+, and another compound that gains H+, and then those roles will become reversed, where acetate functions as the conjugate base of acetic acid, whereas hydronium, because it is losing its H+, functions as the conjugate acid to water, which was the base in the forward reaction. This concludes our introduction and review of acid-base terminology. To make sure that you have a solid understanding of identifying conjugate acid-base pairs, see if you can identify the missing acids and conjugate bases for each of the compounds here, and see if you can draw the conjugate base of pyruvic acid, this acid here, and the conjugate acid of methanamine here. And in the next series of videos, we're going to take these foundations of acids and bases and apply them to specifically equilibrium contexts.